All right. Our second speaker this morning is Wang, who's an assistant professor at Tulane University. And she's going to be telling us about iron speciation, hard trouble saying that, and sedimentary diagenesis revealed by magnetism, and give us some thoughts on, I guess, chemistry and sediments and all that good stuff. So go, Yi.
Yeah.
Thank you.
Thank you. Thank you for the introduction. Very nice. So as Joe mentioned, so literally I'm more of a geochemist, but I did some work on magnetism. And it's very interesting to look from two different perspectives and see like how this, the two things can tell you different information. So I would say this work was actually done at ARM when I was in my PhD. So I would definitely thank everybody at ARM to help me walk through those instruments. That would be so it's like an amazing time. But anyway, before we get started into iron speciation, I want to just briefly talk about like why we care about ocean oxygen, right? Like some people might have seen this a lot in the past, but basically we do care about oxygen because of the marine ecosystem. So go from the top to the bottom, you have very well oxygenated water, right? Like fishes are pretty happy. But as you draw down oxygen, you can imagine some of the macro organisms, especially the benthics like crabs, fish, they will start to feel very stressful to live, to survive, until you reach a point where we call anoxia, which means there is no detectable oxygen in the water. So in that sense, most of the benthic organisms you see here is going to be dead. So on the left, over there, you could actually see, I can see it's my mouse over here. There's like pretty much a paper that's going to show you like the recent intensification of deoxygenation of the ocean. So you see a bunch of blue areas that are open ocean, oxygen minimum zones. So they're kind of natural because there's so much productivity going on over there due to upwelling, but there are also like places where you have those red dots over there. So these are the coastal dead zones. So basically, you're going to have very low oxygen waters in the coastal areas. And we really care about that because the number of dead zones is increasing. So there are a bunch of unknowns because we don't have a lot of instrumental records to look at a bunch of different things like magnitude of longer timescale changes and the mechanisms that are really causing the onset and termination of different deoxygenation events in the past to help us learn more about the future. So transitioning to iron speciation, the reason why we want to use that is because iron can be used as some kind of redox proxy because iron has two different oxidation states, right? So if you look at this redox letter on the right, so apparently oxygen is the most favorable electron acceptor for organic carbon respiration because it gives you the most amount of energy. But as you draw down oxygen, you don't have a lot of choices, right? You're going to go to nitrate first, and then manganese, and then iron. So like the lower oxygen you get, basically the lower redox potential you're going to get, the fewer options you're going to have. So when you go to iron, you will have this iron reduction happening that will give you free iron 2+. And also below that, you have sulfate reduction. This is basically the next resort you can go when you do not have a lot of iron going on. So iron oxyhydroxides really can serve as an electron acceptor of organic carbon respiration, but only in very low oxygen or nearly anoxic conditions in the water. So basically, because we have this reduction of iron and it's coupling with sulfur cycle, so we can have a bunch of iron sulfides that can be preserved in the sediments. So it will give you a bunch of different assemblages of iron minerals in the sediments that you can look at and see, at which point you're going to have more reducing or more like oxidative conditions. So iron speciation, what it does is that it defines something called highly reactive iron. So the thought behind this is that some of the iron minerals can be reduced pretty quickly on the time scale of several months. So that can be That can include ferrihydrite, which is very amorphous, magnetite, goethite, hematite. So there's still some pyrite over there because you can still use pyrite as like an intermediate step for going to pyrite. There's siderite and there's also greigite. So basically, greigite is some still kind of, as Sarah mentioned, some kind of product you can have in your sediments. So with all the highly reactive iron, we could start defining different areas that we think, or geochemists think, that would represent the bottom water conditions. So first of all, we have pyrite iron. So like the ultimate destination of iron sulfides, most stable version, right, is pyrite iron. And there's also some iron sulfides, but the majority of the iron, like we think in the end, will go to pyrite iron if we have enough sulfur or sulfide in the water. And we have highly reactive iron, I just mentioned in the previous slide. And we have something called total iron. So you basically measure the entire box sediment. You get a number of how much iron you have in total. That includes all the iron minerals bound with the iron silicate as well. Okay, so assumption is that, as I mentioned before, the iron oxyhydroxides really completely dissolve in the sulfidic pore waters. When there's hydrogen sulfide around, these should be converted to sulfides, whatever version of sulfides you're looking at. So on the right-hand side, you have this pie plot where which is based on the core top calibration. So what people did is like they sample a bunch of sediment core tops in all kinds of different conditions and measure those parameters and see where dots fall and give you like this kind of threshold that you see here. So on the x-axis, you have highly reactive iron over total iron. On the y-axis, you have pyrite iron over highly reactive iron. So the more highly reactive iron you have, that means probably you have more potential of reducing the iron into pyrite. If you already have a lot of pyrite, that means your water is already very sulfidic. That means there's a lot of sulfide around. So from left to the right, you have oxic conditions. Ferruginous means you have free iron 2+, but you don't have a lot of sulfide around. But as you go up, because you have so much pyrite iron in your sediments, that tells you you have a lot of sulfide that's already in there to help convert your whatever hydroreactive iron into pyrite. So basically 3 zones over here: oxic, ferruginous, and euxidic, and or sulfidic is pretty much means the same. All right, so far so good, hopefully. So one question we have is like, we have this diagram that has been applied a lot in the deep ancient records, but do we actually know much about mineralogy that's actually like behind this, which is super important because geochemistry is blind. It will attack things like without knowing like what iron minerals are really there. But we thought like maybe some other tools can help us to know like what is actually happening. So we went to magnetic measurements because that was something to me, promising that point, and also to my advisor. So this is kind of a summary of a bunch of different iron minerals that we considered, hopefully that we could identify using magnetic measurements. So this is just a summary, and I would mention that before I came to RAM, my application was saying we're trying to find greigite. So even though you're hearing this like diagenetic story, I'll show you the snapshot here. That was my application to RIM. Literally, I'm trying to find a greigite in the Santa Barbara Basin. So we're gonna use like a case study from a very short core that only spanned a few hundred years, basically 250 years. And at that point, we read some papers about greigite preservation during glacial. So we thought that might be a good chance for us to find more in the more recent sediments, and this is why we are here. All right, but I would say we didn't have any very good luck, but I'll tell you some more stories about that in the following slides. So before we go into all the magnetic measurements, I want to show you like where our cores come from. So this is Santa Barbara Basin, basically off Santa Barbara. I see Channel Islands over there. It's like it's a decent basin. It's pretty restricted. So at the bottom, you have very low oxygen. So on the right-hand side, there are a lot of cores that have been taken in that basin. So if you go from the top of the sediments to all the way to 60 centimeters, this is pretty much the depth of the core we're looking at. You see a lot of sulfide at the very beginning, top of the core even. So if you zoom in a little bit more, so the bottom side, you have zooming view of 0 to 10 centimeters. You see like sulfide starts accumulating pretty much in the top 3 centimeters. And you see like iron peaks also pretty early on at or near the sediment water interface. So basically, we have iron reduction that's really shallow, very active iron reduction at the sediment water interface. And you have sulfidic pore waters, which means there's so much sulfide everywhere in depth. You see this is like 100 micromolar. This is very high sulfide in the basin. So our core here is this. So we have a core that has both normal deposition and also some instantaneous depositional events. So you see those varves, very highly laminated. So the good thing for Santa Barbara Basin is like those varves are annual. So you can count the varves and know when you are. So you have 2 flood layers somewhere in the core. So those layers are gray. So you have a lot of terrestrial input because of the floods that actually comes from Ventura River and Santa Clara River over here. So if you are from California, you might have heard the term atmospheric river. So this atmospheric river can dump so much rain within a few days because it's channeling water vapor all the way from the equator. So similar things happened in the past 250 years. Within 250 years, you already had 2 flood layers that actually could be attributed to the atmospheric river that had dumped so much rain in that area that would remobilize so many sediments into the basin. So these layers, even though they are thick, like a few centimeters thick, they are considered instantaneous because they're due to the flood. And we also have a very thick turbidite layer over here. So when we talk about turbidites, if you're from California, again, you might be familiar with earthquakes. There were a lot of earthquakes in the past, and then every time we had an earthquake, you can imagine there's like submarine landslides that would cause a mass accumulation or movement of the sediments that was accumulated somewhere on the slope. So basically, turbidite layer, this one is caused by some submarine landslide that was from 1812 earthquake. It's pretty thick, 8 to 10 centimeters. So it's like you have a very rapid deposition of very thick, large amount of sediments in no time, but probably within a year. So because we have this like normal deposition and some very high sedimentation rate, instantaneous depositional events, this makes it a pretty good target to study both of the redox chemistry of normal time and also some diagenesis that may happen during this like abnormal times of those layers. Alrighty, so we're gonna go into the magnetic measurements. So I'm sure the majority of you are already familiar with all kinds of parameters we're measuring. So basically, the top layer we have magnetic susceptibility, remnant magnetization. So more concentration part, right? Like the first 3 panels are showing you like, what are the concentrations of magnetic minerals. They also tell the same thing. In the top of the core, you have higher concentration. As you go down, you have a very sharp drop somewhere in between, and then pretty much the lowest concentration during the olive layer or the turbidites we talked about, and some very low concentrations during the gray layers too. And next thing we did was like the green size. So single domain, multi-domain. What we see like pretty much the same is like on the top, near the top, you have more of a single domain. And as you go deeper and deeper, you're going towards more multi-domain areas. So the other thing we did was like calculating, how hard that mineral, the magnetic assemblages are. So similar idea from near the core top, it's the most soft part. And as you go down, especially when you have those like events, olive layer, gray layers, they have actually harder magnetic mineral assemblages. So just to summarize what we just talked about, there's a shift of single domain from single domain to like more multi-domain area. So we will show you some fork diagrams in the next slide to show you like how this looks like. So here we go. This is a day plot in the middle and a bunch of different fork diagrams in that core. So on the top we have the pretty much near the core top, 5 to 6 centimeters. You see like a pretty obvious central ridge over here, some active areas over here as well. As you move down, as you turn left counterclockwise, you're moving down from to 15, 16. You can still see that central ridge feature. But as you go down 37, 37, 38, as you can imagine, if you still remember from the previous slide, it's pretty much a big drop of magnetic mineral concentration. You start to go towards this more multi-domain area all the way to 60, 61. You don't see the middle ridge, central ridge anymore. And you have more and more hard magnetic materials going into the sediments as well. So we think basically you have more hematite and goethite as you go deeper. And we also did low temperature cycling. We kind of like differentiating 3 zones, right? Because we have very soft materials on the top and then like transition area, and we have very hard mineral assemblages at the bottom. So what you can see is that there is like a double split near the core top. Basically, more obvious somewhere like in the top 20 centimeters. But as you go down, you lose this feature, basically. You are only moving to this one single peak of the transition. So what we are thinking is like there might be some biogenic magnetite. Of course, we only look at the samples under SEM. We'll show you some SEM figures in a few slides later, but we didn't really look at it under TEM, so we did not really find any magnetofossils in there. At that point, I must admit that I didn't know magnetofossils until I graduated. If I knew that, I would have done this, try to look at TEM to find it. But anyway, so this is definitely what we kind of suspected from the low temperature cycles. So we also see some hump feature over here. So basically what we think based on the different characteristics of magnetic minerals is that we have this hump-shaped feature that is mahimite. So this is not something that geochemists really consider because why would you consider mahimite if you have magnetite, right? We would think like mahimite is pretty much a diagenetic material of magnetic mineral that formed later. We do not know if it's diagenesis or it's like storage issue because the core was not like sealed in the anoxic atmosphere. We stored in 4 degrees C. All right, so just to summarize what we have seen in the past few slides, right? So we have varve sediments, we have gray layers, olive layer, just to remind you what we talked about. So we have mahimite throughout the entire core, and we have some biogenic magnetite that's possible in the upper zone as well. And we have a lot of hematite, probably detrital because of some of the flood input. And we also have pretty high pyrite, actually. There's a super magnetic signal down there as well. So the assumption behind iron speciation, if you still remember from quite a while ago, that I said was like it must dissolve. All the iron oxide hydroxides must dissolve within 6 months. Just to give you a reminder, this core is 250 years. So we still find a lot of iron oxide hydroxides that gas preserved in the self-fitting environments under 100 micromolar sulfide deep in there, even after centuries. So that poses a question of, how efficient or how useful the iron speciation is if your whole assumption of that complete dissolution doesn't really come true in the end, in reality. So I want to show you another thing that makes the iron speciation really problematic is also from those layers. So this is actually our geochemistry data for iron speciation. So on the left-hand side, you have highly reactive iron over total iron. On the right-hand side, you have pyrite iron over highly reactive iron. If you still remember, there are a bunch of thresholds that geochemists have to help you determine the benthic environment of oxygenation. So 0.38 is their magical number, magical threshold to tell you there is anoxic environment in the water. So literally, the majority of the core really doesn't pass this threshold, even though your pore water is pretty sulfidic. Only one point that's really significantly surpassing this threshold, which is on top of the olive layer over here, on the top of turbidites. At the same time, you see the highest amount of pyrite that's actually found in the core. So that gives you an impression that the iron speciation would tell you this layer will be the most reducing layer ever that you see. However, this is not the case that would tell you. So you see like a similar peak of pyrite over gray layers as well. So that makes us wonder what is actually happening. So let's move on here. So we found something called Mokoma right above olive layer over here. If you don't know Mokoma, Mokoma is a bivalve shell. And if you still remember like what we say about low oxygen, bivalves don't like low oxygen. They have to survive in some kind of better oxygen environments. They need to survive, right? So they need oxygen. So if the low oxygen or anoxic or very reducing conditions suggested by iron speciation is true, you would never see Mokoma in the sediments. These are the complete shells, so they were alive, sitting there, doing nothing. So basically, the Mokoma event that's pretty much you can find everywhere in that basin tells you that the oxygen was actually pretty high right after above the olive layer. So what is actually happening? What is going on here? So we call this false positive anoxia for iron speciation because we actually have a lot of new iron mineral coming in due to the submarine landslides. So from this iron magnetic analyses, we know that for those flood layers and turbidites, we actually have a lot of harder materials that got put in instantaneously into the basin, especially those detrital hematite or magnetite. On the other hand, let's see, over there. On the other hand, when you have this large amount of iron oxyhydroxides coming in, you're going to overwhelm a lot of sulfide or react with a lot of sulfide in the water. So what we think is happening is that you're going to have a lot of sulfide oxidation because you have a lot of new iron oxyhydroxides coming in from those turbidites and flood layers. So that kind of like complete consumption of the sulfide really helps to like reduce the amount of sulfide that's like around the water. So that really helps Mokoma to survive. So kind of creates this like very short time scale, which is like a 3-year time scale of the resort for Mokoma to actually occupy the benthic environment. However, you can imagine that when you have a lot of oxidation happening, your iron will be reduced. That means you have a lot of remobilization of iron from iron 3 to iron 2 that will go all the way from the bottom of the olive layer to the surface, right? And apparently, the basin has not stopped sedimentation, right? After that few years, so still like having more and more layers that are dropping in, and you are going to establish the sulfidic environments afterwards. So what's happening here is like you will recapture all of these pyrite later on because you have more sulfide after resuming the normal deposition. So I'll briefly show you some of the SEM photos as well. It might be very dark, so you might not see. So this is a very heterogeneous sediments, right? You see this, there's a diatom over here. There's like a very vague photo of pyrite framboid that Sarah mentioned. So if we zoom in a little bit, so there are a bunch of morphology. You have framboidal pyrite for sure. You also have some large crystals of pyrite, more like octahedral pyrite over there as well. So these are like more rapid formation of pyrite because they don't have time to form this framboidal shape. So a few more photos showing you as you go down, you can see like more and more framboidal pyrite, which is consistent from what we see in the geochemistry as well. So you're likely to see some kind of very concentrated pyrite framboids within like a certain area. What's very interesting is like a lot of the pyrite actually framboids are found in the biogenic residue. So this is a silica shell, which is diatom. So basically, if you do a thin section, you have a diatom opening over here. You see a lot of pyrite growing in the diatoms. So you have more and more frequent occurrences of pyrite down core. But what's more interesting to us is like we're thinking there might be complete sulfate reduction, and because there's so much sulfide oxidation going on. Well, we have some evidence, probably like implied evidence as well. So on the left, you have framboidal pyrite that I just showed you from the last slide within the diatom. This is from a normal deposition. On the right, you have a flat layer. So this is also some diatom shell. And you have very small grain sizes of iron sulfides compared to normal pyrite over there. So we did ADS on that iron sulfides. We think it's a mixture of greigite, even though we didn't find it in magnetic analyses, but a mixture of greigite or pyrite. People also found some very irregular shape of pyrite in that area, in that layer as well. So basically, when you have very small grain size and you have some irregular, less well-developed shapes of the pyrite, that means you're going to have very rapid iron sulfide formation within probably a few months of that deposition. So I will mention that Borowson's group also did sulfur isotopes. So the differences between sulfur isotopes is also extreme. So if you look at some normal deposition, you have biogenic sulfur all the time. That would be like minus 23 per mol. But if you're looking at something in the flat layer that's plus 2 per mol, that means you're using up all the sulfate in that layer because there's so much dense clay in there, and that's all going to be used up for any pyrite formation. Because we do not have enough sulfide to kind of react with all the iron oxyhydroxides, this is where you're going to get some of the greigite formation over there. All right, so main takeaways from what we have done is like we didn't find any greigite from magnetic analyses, but we could see some probably in the SEM. But that also means like we can use magnetic analysis to do something else. It does tell us that there is some biogenic magnetite at the core top, but not in the deep down. And then we know that iron speciation is going to do something very wanky in the instantaneous depositional layers. Very end, 1 minute, and then we're considering doing more Zangs because you see how heterogeneous that is. I'm going to the Zangs area right now, even though I'm doing more manganese. So to look at some of the more in situ identification of the mineralogy and XRFs as well. So what I want to do in the future is like I want to know more about biogenic magnetite preservation. It's on the top. I mean, there's sulfide, but it's not in the deeper core, which is very surprising to me. It's not preserved very well. I don't know if it's reduced first when there's diagenesis or not. And maybe some other magnetic applications in the varying redox fronts, especially like we see in the Santa Barbara Basin or some coastal wetland cores that we can talk about. All right, I think I'm done with my presentation within 30 minutes. Take questions.
Okay, thank you very much.